Hello, this is our first of two lessons on fractions. In this lesson, we're going to look at symmetry, congruent shapes, arrays, and tessellation. Let's move on to the next page. On this page, we have a circle. A circle is a very special shape. It's completely round, and it has infinite lines of symmetry. That means an unlimited number of lines of symmetry. Any line that goes through the center of the circle has a center right in the middle, right about there. Divides the circle into two congruent halves. Congruent means equal in size, and they're the same shape. So same shape, same size. If you look at this semicircle, half circle, it is congruent to the green semicircle. You can see that it completely overlaps the other one. They're exactly the same size. Now, when we use a protractor to draw a circle, let's do that now. I'm going to open a protractor, a full protractor. Some protractors are full and some are half. For this one, I want to show you using a full protractor. Let me show you what an arc is. An arc is part of the circumference of the circle. Look at that black line that goes around. So the arc would be part of that, a fraction of that full circumference. Now, if I'm drawing a line, I'm going to choose a line that is easy for you to see. I'm going to switch to white. So if you look carefully, you see 0 there. They're numbered both ways. So if I go like that, I have a curved line that goes all the way around if I draw it. But instead of going all the way around, I only went to 90 degrees, which means this is a quarter of the way. Okay, and I'm going to switch my color to a different color for you to better see. Not green, how about yellow? Or yeah, yellow is good. So I'm going to go from here, and you can see I drew a curved line that goes halfway. So I don't know if you can see well, but you could also, instead of drawing an arc, you could do a closed arc or a filled arc. And let's switch to blue. So if I'm doing a filled arc, so what I have here, you can see that's a quarter, that's 90 degrees going the other way. Now I'm going to put that away. So you see that arc there? There's another arc there. That's curved line. And this is a filled arc, and it's blue. That's a quarter. Let's move on to the next page. We have a few circles here. This is the full circle. Going all the way around is 360 degrees. Now when we cut the circle in halves, so we get two halves, each one has 180 degrees. This is called a straight line because it looks like a straight line. Okay, 180 degrees this way, 180 degrees this way. It is called also a half turn. A full turn is 360 degrees. A half turn is 180 degrees. So this is a half a circle. Let's go on to a third of a circle. A third is 120 degrees. 360 degrees divided by 3 is 120 degrees. So that's, it looks like a Mercedes-Benz sign. The Mercedes-Benz car sign kind of looks like that. And if we divide the circle into 4 equal or congruent parts, we get filled arcs that are 90 degrees. So you can see this, the 90-degree angle or a square corner. You can see that there. So 1, 2, 3, 4. And you can see they're congruent because if I do that, you can see they match perfectly, all of them. So we know they're congruent. So if I do that one as well, you can see they are congruent. They're the same. Okay, makes sense? Let's go back. So you can see they're the same. And 1/5 of 360 degrees is 72 degrees. So that's 1/5 of the circle. Let's move on to the next page. Here I have 1/6 of the circle. Each section is 1/6, so that's 1/6. So I have 6 of them. So these are all 1/6 each. And 36 divided by 6 is 6. So 360 degrees divided by 6 is 60 degrees. So these are all 60 degrees. And you can see that. Let's move this out so it's too crowded there. Okay, so that's 60 degrees. Now you can think of a hexagon here, and each hexagon has, you can see the hexagon has 6 equilateral triangles. You can see that's 60 degrees, 60 degrees, 60 degrees. And we learned that equilateral triangles have angles that are 60 degrees inside. They're the same. 3 angles, all the same. And you can imagine it inside. Let's move on to the next page. Sometimes, for example, when you're looking at circle graphs or pie charts, not all your pieces are the same, but you still need to recognize different fractions of the circle. So how do you do that? For me, the most important thing is to look at what I call anchor fractions. What do I mean by that? Now, everybody can tell this is a half. So this is simple. So because, look at that, it's a straight angle, straight line goes right through the middle. So we know it is 180 degrees. So that's that. Now, do we have any more like that? Yes, we have it here. So that's also 180 degrees. Do I have more? Yes, I have one more here. So that's a half. Step by step, we're going to figure out. Now, obviously, if you have a protractor, you can measure it. And sometimes you might not have. And I thought maybe you don't have one at home. That's why I'm trying to show you ways to figure out without actually using a protractor. But the best way is to measure it correctly with a protractor. Now, here, we did all the half circles. Now, we have to look at the other easy ones. The other easy ones is a quarter. Remember, a quarter of a circle has a right angle in there. So I have one here. Do you see the right angle right there? Do you see the L angle there? Do you see that? 90 degrees. So this, we know this is 90 degrees. We know that's a quarter. I need 4 of these to fill the whole circle. That's why we call it a quarter. And here, do I have any more quarter? Yeah, I have one here. So that's 90 degrees. And I have one more here. And that's 90 degrees. Right there. Okay. The rest is a little bit harder, but not really. Let's look at this one. If these two together are a quarter, remember? Together, they're just like this. A quarter. Now, they are equal in size, so it's like if you have a quarter and you cut it in half, you get 1/8. So each one is 1/8. So, and which means it's 45 degrees in there. And what's left? Let's look at, oh, we have this one. This is also not too hard to figure out. This is 3 pieces make a half, so they should be, I need 6 of these to fill the whole thing. So that's 1/6, which is 60 degrees. 1/6 and 1/6, and they're all 60 degrees each. Okay, now we did all of these. This is a little bit harder. Well, let's see. Okay, I don't know if you see. Remember the Mercedes-Benz sign? Do you see that? It looks like a third sign here. So this to me is a third. I can actually measure it to prove it to you. Okay, that's a third. These two together are a third, and it looks like that. Do you see that? Do you see these two are the same as these two? So these are 1/6 each. They should be 60 degrees if you measure this angle here and this angle here. So that's 60 degrees as well. Now, all these together should be 180, right? So this is half the circle, so this should be 30 degrees. So that's 30 degrees, which is 1/12. Remember, 360 divided by 30 is 12. And so we finished that. The only one left is this. It seems that, watch this one. It seems that a quarter of the circle was divided into 3 pieces. I don't know if you see. So if you imagine 3 sections makes 90. So this is 30. So that's 1/12. This one is the same as that. Do you see that? They're the same. 30 degrees. Again, you can measure them to verify. And this is exactly the same as that. Double this. We saw that it was a double of this. So that's 60 degrees or 1/6. Now, as I said, the best way to do it is to measure using a protractor. And to do that, to use a protractor, let me show you how you do that. When you use a protractor, you have to make sure your protractor is middle. If it's a, I'm going to switch to a half protractor for you. So it's easy. Most of protractors are half, the ones you get. And so this is a full half. And then when you get a protractor, it's important that you put that middle point at the bottom. So let's say I want to measure this 30 degrees. You align it with the corner and align one line to the 0 or the one side of the angle. So I'm going to find how I turn this because I have too many things going on here. So I'm looking for, yeah, there it is. So here we are. If you look carefully, that's 0, 10, 20, 30. So I went, remember this line matches the bottom line here on the protractor. The corner is right there, matches the corner of the angle. And the second line, or the ray line, goes over 30. So you have to count from 0 because protractors usually are numbered both ways. So you count from 0, 0, 10, 20, 30. So that's 30 degrees. So measuring with a protractor is the final proof. A lot of times for these anchor fractions, you can actually judge them by the eye and you can tell them, okay, if you don't have a protractor. Let's move on to the next page. We're going to move on to a triangle. This one is a special triangle, the equilateral triangle. It has 3 lines of symmetry. Each line of symmetry divides the shape into 2 congruent halves. That means if you fold the triangle along its line of symmetry, the 2 halves match perfectly. For example, this half and this half, when folded, match perfectly, and so on. So this is a half, this is a half. You could also divide an equilateral triangle into three congruent parts. Here we have 1/3 red, 1/3 red here. If you look carefully, these lines actually go on the lines of symmetry. So that is why you need to know lines of symmetry when you want to divide shapes into equal fractions. So let's move on to the next page. Same shape, we have an equilateral triangles. Here is a third, a third. This one is a fourth. You can see that actually this is a net for a triangular pyramid, and remember we made that in class as well. Now when you can combine these together, for example, look at this, is that 4 triangles, but inside each triangle I put one of these in there. So 4 times 4 times 3 is 12. So this is 1/12 of the whole shape. And this one I made this, which is that, and I put these in each triangle. So it's again 4 times 3. I get a different pattern, but the fraction is the same, 1/12. And here I put these inside each. So 4 times 4 is 16. I have 16. So 1 would be 1/16. 2 would be 2/16, and so on. Now, a lot of times students get confused. And for example, if I give them this question, they think that's 1/3, or they think this is 1/4. But you have to ask yourself, fraction is about equal parts. Are these equal? I don't think so, and you know it's not. So if you make a cookie in the shape of a triangle, you wouldn't want to get this piece. This piece is too small. Look at that. Look at that. The bottom piece is like 5 times the size of the top piece. We know, we can't tell what fraction it is, but we can tell something. We can tell that this section is much bigger than 1/3. We know that. We don't know what fraction it is, but we do know this was not divided equally, and we do know this is more than 1/3. And here we have the same problem. Look at that. The bottom sides is like double the top side. So that's not fair. That's not doing it properly, because I didn't divide them equally. We don't know what fraction they are because they're all different sizes. These two are the same, these two are the same, but they're different sizes. But we do know this is much less than a quarter. We know this is this is not 1/4, this is less than 1/4. We know that for sure. And let's look at a square. Square is a regular polygon, just like a equilateral triangle. That means all sides are equal. All angles are the same, equal as well. Now, regular polygons have the same number of lines of symmetry as the number of sides. So 4-sided shape, this one is a regular. Regular means all sides are equal, or all angles are equal. So it has 4 lines of symmetry. They're here. Now, I can divide my square into 4 equal pieces, 4 triangles or 4 squares, or use all my lines of symmetry and make 8 congruent triangles inside. They're all the same. Now, squares and rectangles are interesting because you can actually divide them any way you want, because you can just, for example, here I divided it this way into 3 parts that are equal. All you have to do is measuring these sides to make sure they're equal. So this is 1/3, and here this is 1/5. Let's move on to the next page. And that is how you can tessellate. Tessellate means tiling. When you can put shapes together to cover an area completely without overlap and without gaps, that is called tessellation. If you look at your bathroom wall, often you see tiles there, and those tiles are square or rectangular. They tessellate because their angles are 90 degrees. So you can put four of them together, so 90, 90, 90, 90, 100, 180, then 360. So they fit together perfectly. So rectangles and squares can tessellate easily, and they're easy to work with. That's why you see tiles on the floor or on the wall, and they're made of rectangular or square pieces. Here we're also looking at arrays, and we talked about that already. Now if you look at these, what do you have in common here? Well, this is 2/6. In arrays, you can find how many pieces using multiplication. So 3 rows of 2, that's 6. 3 times 2. Here 3 times 1, that's 3. 3 times 4, 12. 3 times 5 equals 15. One thing you might have noticed is that these fractions are actually equal or equivalent. You can see 2/6 is the same as 1/3, is the same as 5/15, and is the same as 4/12. They're all the same. They're all equivalent or equal. The reason is they're the same ratio. For example, 1 times 3 is 3. So 3 times 2 is 6. 3 times 5 is 15. 3 times 4 equals 12. So they're the same ratio, the same fraction. Let's move on to the next one. Now, arrays are very useful because you can use multiplication to count them quickly. So here, for example, I have an array of 6 by 4, 6 rows, 4 columns. There are 24 little tiles here. So I have 4 24ths or 1/6 of this shape is green. 8 24ths are kind of pink purplish, and 12 24ths are yellow, which is actually a half. 12 is half of 24. 6 rows of 4. That's what an array is when you put them in rows and columns. Let's move on to another one. This one is different. Here we have 6 rows of 5. We have 30 tiles here. So the bottom number or the denominator is 30. That's the total. Remember, the bottom number is always the total. It's called the denominator. So 6 30ths are green. 22 30ths are yellow. 2 30ths are reddish or purplish. And let's move on to the next. Here we have 6 rows of 8, so 48 in total. So the denominator is 48, and we count the green ones. Again, we can use multiplication to help us. 1 2 3 4. 4 times 6 is 24. 24 48. Again, that is a half as well. 24 is half of 48. 4 48s here, and 20 48s are yellow. Let's move on to the next. We have a regular pentagon. Again, a regular polygon, all sides, all angles are the same. And a regular pentagon has 5 lines of symmetry, and I drew them here. When you draw them all, you get 10 pieces in there because each line of symmetry divides the shape into 2 halves. So 5 times 2 is 10. So this is 1/10. That piece, that tile is 1/10. And this is 1/5. This one. And remember, this is the center, again, the center of the pentagon. That's important. And it's when the lines of, where the lines of symmetry cross, they create the center. The center is right there. That's important to know. Let's move on to the next page. We have 2 shapes. They're not divided equally. We can tell by looking at them. They look off. they don't look right. So remember, the lines of symmetry go from corners. They go from corners to the middle of the opposite side, something like that. And so something like that, we know that this is not the center. The center is lower, so it's messed up. We don't know what fraction these are, but we do know one thing. We know this is less than 1/5. We know this is more than 1/5. We know that because if I get a piece there and try to put it in there, we know it's less. We know it's less. We know this is more than that. And we know this is less. We know that for a fact. You can see it's less. So even sometimes when you don't know, there are things you do know. So you need to rely on those. Here, again, remember, sometimes we don't have all the pieces the same size. So somebody might think 1, 2, 3, 4 pieces, so that's 1/4. Well, that's wrong. It cannot be 1/4. The pieces are different sizes, so each one is different. We know this is a half. This is a line of symmetry, so that's a half. We know this is a fifth. Do you remember here? Each side connected to the middle makes 1/5. This is also 1/5. This is half of that. That's 1/10. And if you look back, you can see what I'm talking about. This is 1/10. This is 1/5. So it's good to know. Now let's look at hexagons. I love hexagons. A hexagon, a regular hexagon, has 6 lines of symmetry. Irregular means all sides equal. All angles here are equal as well. That's what a regular polygon is. Sides equal, angles are equal. So here I have, for example, this would be 1/12 of this hexagon. You can split the hexagon into 2 congruent pentagon like this, 2 congruent trapezoid like this, 3 rhombi or rhombuses like this, 3 pentagons like this. There are different ways you can do it, but if you notice, all these lines follow these lines of symmetry. So that's why I introduced symmetry here when looking at fractions, because it's important to make your pieces equal. That's very important. So let's move on to the next. So if I look at this one, I know this line is not in the middle. It should have been there. So I don't know what fraction this is. I don't know what fraction this is, but I do know this is less than 1/2, and I do know this is more than 1/2. Here, the center is not there. Remember, connecting opposite points makes a line of symmetry, so that center should be there, somewhere there, along this line, somewhere there. So this I know is bigger than 1/3. I know this is 1/3. It's not 1/3, it's less than 1/3. Here again, the center is somewhere down here. So I know this is it's not 1/3, it's less than 1/3. This is greater than 1/3. So these are the things I do know. Now, if you look at a hexagon, it can be divided into 4 trapezoids, right angle trapezoid like this. They're all equal, they're all congruent. 6 triangles like this. 6 triangles like this. They're getting more interesting. 12 triangles like this, so each section is 1/12. And also 12 triangles. They're actually the same type of triangles, believe it or not. So if you look at that one, you can see it's identical to that one. It's just the arrangement is different. And it just makes interesting shapes. You can see a triangle inside the hexagon. Let's move on to the next. Here again, we have a mix of fractions, so we can't just count, say 1, 2, 3, 4, 5, 6. So this is 1/6. We cannot do that because the pieces are not the same size. So we have to kind of measure them in a sense based on what we know. Okay, so we know, for example, this is 1/3. Remember, 3 rhombuses make the hexagon. This is 1/3. This is 1/6. This is 1/6. This is 1/6. Now this is half of 1/6, so that's 1/12. This is just like that. The rhombus is 1/3. The trapezoid is the half. You saw that on the other page. This is 1/6. So you need to know how they look like and what fraction they are. Okay, so let's go on to the next page. Same idea. That's a half, the trapezoid. This is a quarter, 1/12, 1/6. Actually, if you add all these fractions, you should get a whole. Okay, let's move on to the next. Now, we talked about tessellation, remember, with tiles, but with tessellation, you don't need square tiles. They're easy for tessellation, but you can use triangles for tessellation. Here, we're using triangles here. Each one is 1/48th of this design. And how do I figure that out? So look, I have 4 hexagons, one here, one there, one there, and one there. Each hexagon has 12 triangles inside, so that's 1/48th of the whole design. So I could ask you what fraction is red. You could say 4/48th, or you could say 1/12th, right? Because the ratio doesn't, if you repeat a pattern, the ratio doesn't change. You get more pieces, but then the total pieces also increase by the same factor. Here I have another interesting design. Again, this is tessellation. I used parallelograms here. Now, if you look, I have 5 hexagons, 1, 2, 3, 4, 5. And each hexagon has 6 parallelograms. So 5 times 6 is 30. So that's 1/30th of the whole design. Let's move on to the next. 2 tessellations here. I have here a hexagon. Inside the hexagon, I have 6 triangles. And each triangle has 3 kites. Kites are 4-sided shapes, so this side and this side are equal, this and this are equal. Okay, so 6 times 3 is 18, so that's 1/18th. Here I have 6 triangles. If you can see, each triangle has 4 triangles inside, so that's 6 times 4 is 24. That's 1/24th, and that's why multiplication is really useful. A lot of times you don't want to count because there might be too many and it gets confusing and it's hard to count, especially on these patterns. It's hard to count. Let's move on to the next. Again, let's find a trick. I have 1, 2, 3, 4 hexagons. So 4 hexagons. Each hexagon has 6 triangles inside. 1, 2, 3, 4, 5, 6. Each triangle has 3 kites in there. So 4 times 6 times 3 is 72. You can use a calculator, but you can also do it in your head. I would do 6 times 3 is 18. Anything times 4 is double. 18 double 36. 36 double 72. That's the way I do it in my head. You can do it. There are different strategies. You might find a different strategy easier. That's okay. So let's look at this one. You can see how confusing it gets. You can't really count them. You could, it's just too hard. So here I have 5 hexagons here. Each hexagon has 6 triangles. 1, 2, 3, 4, 5, 6. Each triangle has 4 triangles inside. So 5 times 6 times 4. Again, this is not that hard. 6 times 4 is 24. Anything times 5, you can actually multiply it by 10 and divide it by 2, or divide by 2, multiply by 10. So 6 times 4 is 24. Half of that is 12. 12 times 10 is 120. So you can do it in your head a lot of times. So this is 1/20th of this design. Again, this is a type of tessellation. Let's move on to the next page. Here I just have a mishmash of different tiles and tessellating them together. They're interesting. Tessellation doesn't have to be geometric. It could be different shapes. You know, artists use all kinds of natural shapes like dogs, cats, and they can tessellate them together. And maybe I'll do a lesson on that another time. They are interesting, they're beautiful, they're both math and art. Thanks so much for watching. I'm going to tell you, show you a preview of our next lesson. Our next lesson, we're going to look at fractions of a set, factor pairs, arrays, multiplication, and division. It's a continuation of this lesson. So thank you so much for watching, and take care. See you later.